Well, good morning. It's Tuesday, the 2nd. Today we're going to be on section 28. First, here's a warm-up based a little bit off what we did yesterday. So here we are told that we have a function defined to be the integral from 0 to x of f of t dt. H of x is an integral defined function. We are asked what is the correct order for h of 2, h prime of 2, and h double prime of 2? Well, in order to do so, we would need to know what h prime of x is and h double prime of x. So to find that, let's first do, we're going to first take the derivative of this. And when we take the derivative of that, we're going to get the h prime of x. Based on the second fundamental theorem of calculus, will just equal that x just goes in there, f of x. Which would then mean that h prime of 2 is f of 2, which according to the graph is 0. Okay, that's helpful. And that'll also mean that if we want h double prime of x, well, then that would just be f prime of x. And then that would mean h double prime of 2, which is f prime of 2. We don't know its actual value. We don't. But one thing we do know is that since it's going down and decreasing at 2, the slope, if I drew a tangent line, is definitely negative. We can tell that it is negative, that h double prime of 2 is less than 0. And h of 2, which represents the integral from 0 to 2 of x. Well, the integral from 0 to 2 of f, that means the area under f starting at 0 and ending at 2, meaning that entire area there. Well, that is all positive area. That is all positive area. We don't know its actual value, but we do know that it is positive. So I could say that that is greater than 0. And based on those three things, we can get that the answer will have h double prime of 2 being the least and h of 2 being the most. Which doesn't seem to be there. Is there a choice E that's not showing? Oh, there is. It's choice E that wasn't showing. It would be this one then. Because h prime of 2 ends up in the middle, it being 0. H double prime is negative, so it's the least, and h of 2 is a positive area, and so it ends up as the most. Okay, so that was our warm-up. A few reminders. Here's our Schoology page, and integration homework 2, which, apparently Lauren's already turned it in, that's good, is sections 30, 31, 32, and then the topic 6.10 skill builder from Friday, and it is due today, Tuesday, February 2nd. So that's integration homework 2. Integration homework 3, we started that stuff yesterday, is second fundamental theorem calculus worksheet, section 28 that we're doing today, average value that we're doing tomorrow, and then the circuit that we're doing on Friday. And that is due next Tuesday, February 9th, the review day. Okay, now let's move on to section 28. Section 28. Several people did ask me to do some problems, but like yesterday, I'm going to wait till the end to get the lesson done first, then I'll hit some of those. So very similar to the warm-up and what we did yesterday, we're talking about functions that are from a number to x, functions that are numbers to x. Those functions are called either accumulation functions or area functions or integral functions, stuff like that. So starting off with the idea that a definite integral is really just nothing more than the area under the function, and it can be considered a very special type of problem. So if we have f of x just equals 2, then we have this horizontal line there. Well, we know that that horizontal line to the right, it's going to be the same as f of t equals 2 or f of k equals 2, it doesn't matter the independent variable that you call it, whether it's x, t, or k, or any other variable, independent variable, it doesn't matter. It's still going to cause a horizontal line. Okay, we're just used to using x. So the purpose of what we're going to do next, we're going to use the graph, and we're going to consider the expression, the integral from 0 to x of f of t dt. And that is a function of x. That is a function of x. I could call that integral, like the previous problem, I could set that integral equal to h of x, like that. It becomes a function of x because it will change depending on what the x value is, get bigger or smaller. This being an integral function, its output tells us the area underneath f. Its input is where we are along the x-axis, and its output tells us what the area is underneath f, because the function is a definite integral. So it represents the area underneath f, starting at 0 until you get to whatever that x value is. So as x changes, the integral would change. You would get more area or less area depending on what kind of curve the function is. That up there. So here in this table, we're going to fill out what the integral would be at each x value. Well, at the x value of 0, that would end up meaning the integral from 0 to 0 of f of t dt. Well, that would end up being 0 then, no area. But if we put the next x value of 1, and go from 0 to 1 of f dt. If we go and look at our graph here, and go from 0 to 1, well, that's just that rectangle, so it'll be 2. Then integral from 0 to, I have a 2 up there now, integral from 0 to 2 of f of t dt. Well, that would just add another rectangle. And now the rectangle that I added also has an area of 2. So we would now have 4 there. And then with 3, that would add another rectangle, which also has, each of these rectangles has an area of 2, but I'm just adding along. So then now once x is 3, the area from 0 to 3 is 6. It'll be 8, and it'll be 10. So we do end up getting that as x gets larger, the area under the function gets larger. So the integral from 0 to x would increase as well. We are accumulating area. And so we will call the expression integral from 0 to x of f t dt an accumulation function. We call it an accumulation function. Instead of an accumulation function, it's sometimes called a area function. Either accumulation function or area function. An integral from 0 to x being a function is sometimes called a area function, but accumulation function is the better term. So we do get that, should appear that for f of t equaling 2, or f of x equaling 2, the integral from 0 to x of f of x dx so like I said earlier, we could, since it is a function itself, we could define that function to be h of x, just some function. We could define that to be a function. Well, based on what's happening here, we're adding 2 each time, 2, 4, 6, 8, 10. So based on that, that h of x, which I've defined to be that integral, ends up being just 2x. Which hopefully makes sense because we do know how to take integrals, we do know how to take antiderivatives, and our function was just 2. And what's the antiderivative of 2? It's 2x. Or another reason why, based on what we discussed yesterday, the derivative of an integral should be the function itself. The derivative of the integral should be the function itself. So if I take the derivative of this integral, I should just get 2. Well, if I have defined this function to be the integral, And if its derivative is supposed to give me 2, then that function must be 2x. Let's look at a slightly different one. So here we have f of x equaling 2. No, sorry, equaling 2x. So f of x equals 2x. And we want to count the values, calculate the values of the accumulation function starting at x equals 0 until we get to x equals 4. Well, at x equals 0, it would be 0 again. But x equals 1, we would end up having this triangle there, which would be 1 by, notice the graph, it's going up by 2 each time the y-axis is up by 2. So it's 1 by 2 divided by 2, which would be 1. And then f of 2 would be the area from 0 to 2. So that's a bigger triangle. Well, now the base is 2 and the height is 4. So it'd be 2 times 4 divided by 2, which is 4. And then for when x is 3, it'd be the triangle all the way to 3 underneath the curve, which has a base of 3 and a height of 6. 3 times 6, 18 divided by 2 is 9. Well, anyone want to guess what would come next? 0, 1, 4, 9. Well, these are all perfect squares so far. It's going to be 16. And that should also make sense in that if our function is 2x, like what happened on the previous one, the accumulation function just ends up being the integral of the function we're taking the area of. So what's the integral of 2x? It is x squared, which is what happens there. So if we then plotted those points there, like this is asking, that's 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. That's why they had it like this. It is just the function x squared. Now, if we were to take the derivative of this integral, well, we just said that that integral just is x squared. So if we take the derivative of the integral, which is x squared, we're going to get 2x, which is what's supposed to happen based on what we discussed yesterday with second fundamental theorem of calculus, that if you take the derivative of an integral, you just get the function as is, and that function is 2x. And this right here, derivative of the integral from 0 to x of t dt equaling f of x, that is the second fundamental theorem of calculus that we discussed yesterday. That says we'll discuss it later. I thought it made more sense to discuss it previously. Let's look at the next page. So here we have a more complicated looking graph, f of t, and we're told that capital F is going to equal the integral from 0 to x of f of t dt. And so that we have defined a function to be an integral. So again, that is a accumulation function, or also called an area function or an integral function. It outputs the area or accumulated area underneath the graph from 0 until you get to the x value. Now, it doesn't always have to be a 0 at the bottom. Accumulation functions or area functions are defined however they're defined. Like they could be defined differently on every different problem. That lower limit could be 3 if it wanted to be. Just depends on how people who make up the problem set up the problem. So what's happening here in this problem is we've f of x, f of t, same idea. To make this easier to understand, we're going to have it be an actual scenario, and f of t is going to be the rate of snow accumulation over an 8-hour period. Rate of snow accumulation over an 8-hour period. So the x-axis is t time in hours. So for instance, what this means is that at time 1, snow is falling at a rate of 3 inches per hour. Notice time 1, it's at 3 up here. So they are having the y values of this function be the rate of snowfall. The y values are the rate of snowfall. So then when we start calculating the integral of the rate, so the y values here are the rate of snowfall in inches per hour. When we get the area, so the y values are in inches per hour. when we start getting the area under the function, we would be doing inches per hour times hours, and that's just going to give us inches. That is just going to give us inches. So the area under this function represents the accumulated amount of inches at each time. The accumulated amount of inches of snow at each time. So then at time 3, it's not snowing at all at that moment. At time 3, the rate of snowfall is 0. But at time 4, it's melting at 4 inches per hour. And we can say it's melting because the rate of snowfall is actually -4. And so the rate at which snow is accumulating is negative, meaning we must be losing snow at that time. So if we start calculating this from time 0, we have 0 snow there. And then that part will be 2, 3, 2 plus 3 will then be 5. And the integral from 0 to 3, that this piece here is 3 halves. So 3 halves plus 5. No, I'm just going to put it's 1.5. So I'm going to put 6.5 there then. Then at 4, that's then this triangle here, which is going to be a -2 area. So we're going to go down to 4.5. So we've lost 2 inches of snow between time 3 and time 4. And then this piece here, that's also a -2. So we've lost another 2 inches of snow between time 4 and time 5. Then at time 5, there's 0 rate again, but then from time 5 to time 6.5, the snow starts falling again. Snow starts falling again, such that at time 6, it's falling at 1 inch per hour. So we do gain another ½ inch of snow there. So that would go up to 3 then. I don't know why I wrote 6. Then at 6.5, we have then 3.25. But then in this little piece, we lose another quarter of an hour. I mean, not a quarter of an hour, a quarter inch of snow. So back down to 3. And then we lose another 1 inch of snow there. So down to 2. That's just accumulating the area underneath the function. Now, they've defined that accumulation function to be the capital F of x. Well, we've seen that the derivative of the integral will just be the function as is. So then capital F of x, which equals the integral, it would follow that capital F prime would just be f. Capital F prime would just be f, which makes sense based on the second fundamental theorem. So capital F prime, which is the derivative of the integral, is just f. So this table here is just asking for the y values of the function that they gave us. It's just asking for the y values of the function they gave us. Because what has happened is this function that they gave us here, this f of t, that equals capital F prime of t. That equals capital F prime of t. So what we have here is we have a derivative graph, meaning everything that we discussed in the fall semester dealing with function analysis, where we have increasing and decreasing functions, max, min, points of concavity, points of inflection, concavity, all of that is going to be applied here in this section as well. Because when we have an original function, when we have a function and we have defined some function to be an accumulation function, then the function that we have is really a derivative graph. The function we have is a derivative graph. It is the derivative of capital F. So then, when we fill out this table here, capital F prime, which is the derivative of the accumulation function, derivative of the integral, is just lowercase f, meaning capital F prime of 0 would be lowercase f of 0, and f of 0 is 1. And then we would have next 3, and then 3, and then 0, negative 4, then 0, then 1, 0, negative 1, negative 1. And so these down here, these are all values of the derivative at each of the x values above. Then part C is asking us, as I just discussed, remember that capital F will be increasing and decreasing, as well as have relative extrema. To figure those stuff out, we'd have to look at capital F prime. Well, capital F prime is just the lowercase f graph that they gave us. So what I'm going to do right here with this table we made, let's do a sign chart. Well, we see that it's 0 here, it's positive here, then it's negative, then it's 0 again, then it's positive, then it's 0 again, then it's negative. So based on that sign chart of f prime, which is just the lowercase f graph that they gave us, we can determine whether where it's increasing, decreasing, and where we have relative maxes and mins. So based on that, capital F is increasing from 0 to 3, and then it's increasing again from 5 to 6.5. And then it is decreasing from 3 to 5, and then again from 6.5 to 8. We're gonna have a hard bracket on the 8 because that's where it ends. And based on this, we do also see that we have a relative max where we switch from increasing to decreasing, which is where we switch from f prime being positive to f prime being negative. So we actually have two relative maxes. With relative max at x equals 3, at x equals 3, f prime switches from positive to negative, and then again at 6.5. And we have a relative min at x equals 5. Because at x equals 5 is where we switch from being negative to positive, when f prime switches from negative to positive. Okay, and then what they want us to do on D is use info about f double prime to determine concavity as well as points of inflection. So we're going to make our own number line here. Make that end be 8, this end be 0. Okay, well, first off, what are some important points about f double prime? Capital F double prime. Well, capital F prime is just lowercase f, which would then mean that capital F double prime is lowercase f prime, meaning it's going to be the slopes of the graph that they gave us. It's the derivative of the graph they gave us. So if we go back up and look at this graph, anywhere where this graph is 0 or anywhere where the slopes are 0 or undefined is going to be an important point for our inflection, for our f double prime. So from 1 to 2, the slope is 0. At 4, we have a sharp corner, so it's undefined there. At 6, we got a sharp corner, and then 7 to 8, 0 again. Yes, I know there's some other corners, but none of the other corners does it change from being positive to negative or negative to positive. So 7, okay, it's 0 in that section from 7 to 8. I'm going to just zoom out real quick so I can get this done quickly. So you can see the graph at the same time. So 2 to 3. 2 to 3. It's 0 in that section. Then at 5. Oh no, not 2 to 3, 1 to 2. From 1 to 2, it's 0. Before 1, it's positive. From 2 to 4, it's a negative slope. At 4, we have a corner, I say undefined. Then from 4 to 6, we have a positive slope. Then 6 to 7, negative again. Okay, so based on that, we are concave up from 0 to 1, and from 4 to 6. We are concave down from 2 to 4, and from 6 to 7. And we have inflection points, x equals, from at 1, it switches from positive concavity to no concavity, so that's not an inflection point. And similarly at 2, but at 4 and at 6 is switching signs. So double prime does switch signs at 4 and 6. Okay, and then I'm not going to worry about graphing it. You're not going to have to graph. So the next page, very similar stuff's happening on this page. How much time do I have left? Oh, still 24 minutes. Awesome. It didn't take long as I thought. Okay, so they have defined for us to be capital F of x equals this integral function from 0 to x of f of t dt. And so capital F is the area under the function. Capital F is the area under the function from 0 until the x value. From 0 until the x value. Meaning f of 0 would mean the integral from 0 to 0, which would be 0 then. Capital F of 2 would mean the integral from 0 to 2 of f. Don't know why I paused there. Integral from 0 to 2 of f. Well, that would mean the area underneath that. Okay, well, that would end up being a quarter of a circle where the radius is 2, meaning it will be pi times 2 squared divided by 4. 2 squared is 4 over 4. Would just be 1, so this would be pi. Okay, then capital F of 4, well, that'd add another pi, so it'll be 2 pi. And then capital F of 6, so we have pi there, we got another pi there. Capital F of 6 would then be the integral from 0 until 6, so the area underneath the function, starting at 0, ending at 6. Okay, so we're still going to have that 2 pi, but we now have to subtract this area. This area over here is 2. Capital F of 6 would be 2 pi minus 2. Okay, so again, all the capital F's, that's the integral function. Capital F of negative 1. Okay, this aspect right here, capital F of negative 1, negative 2, negative 3, negative 4, this was a common mistake on BC's test last week. This was a common mistake on BC's test because I mean, they just found the positive area and didn't think about the fact that they're going backwards when they're doing this, because this f of -1 goes from 0 to -1. Okay. So that area is a 1 area, but we're going backwards. So it'll be a -1. Or to better understand that, one definite integration rule that we use a lot is we throw negative in front, then we flip it to make it go from left to right, from 1 to 0. The integral from -1 to 0 is 1, then you have the negative in front. So similarly, capital F of -2, that would be the integral from 0 to -2 of f, which you could put the negative in front, flip it to be -2 to 0. Integral from -2 to 0, it's still going to have that 1, and then you got that rectangle, which is 2. So then that's going to end up being -3. Capital F of -3, well, that's still going to be -3. Because using still going to be -3 is we have this little red triangle I just made. That is going to be a, well, 2 times a half is 1 times another half is, okay, that's a half. That is 1/2. And then this piece on there, that's also 1/2. And those are going to cancel. Those are going to cancel. So then once you get all the way to 3, then the integral from -3 to -2 ends up being 0 because those cancel. So you just still have the same amount of area. And then that last piece, go from negative to -4 would be 0 to -4. Or you could throw a negative in front and go from -4 to 0 of f. Okay, from -4 all the way to 0. Well, that section cancels. That's 3. And this is a -1 times 2 is 2 divided by 2 is 1. That's a -1 area. So we're going to have, so then we would have that negative times, okay, that's -1, 0 section, and wait, no, that, and 3. So the 2. So -2 is that whole piece. Now the next section of this wants us to find capital F prime of 4, capital F prime of 2, capital F prime of 5, and so on. Well, capital F prime of 4, that means F prime of 4, lowercase f prime of 4. Lowercase f prime of 4 is 0. Because, go back up and show that again. So, well, they've defined the integral function or accumulation function to be capital F of x, which would then mean that if I take the derivative of that whole thing, dx, we would just end up getting a lowercase f of x. So this lowercase f of x here, that is capital F prime of x. Well, then that would also mean, it will be necessary, capital F double prime of x is lowercase f prime. So based on that, f of capital F prime of 4 is really just lowercase f of 4, which is 0. So then capital F prime of 2 is lowercase f of 2, which is 2. Capital F prime of 6 is lowercase f of 6, which is -2. Capital F prime of 5 is lowercase f 5, which is -1. And then the next section, these are all double primes. These are all double primes, so it's after the slope. Well, capital F double prime of 2, that means f prime of 2. Well, that's at the top of that. That's at a peak. That's a horizontal tangent. So that's going to be 0. Capital F double prime of 5. So that means the slope, that's going to be lowercase f prime of 5. So the slope of f when x is 5. Well, that's a -1 slope there. And then capital F double prime of -0.5. -0.5. Change colors real quick. So that's asking for lowercase f prime of -0.5. So the slope at this point there, well, that's a -2 slope. Capital F double prime of 0. Got a sharp corner cusp. So that's going to be undefined or does not exist. And then, based on all of that, we're going to figure out whether things are increasing, decreasing, max, min, concavity. Well, to do so, I'm going to make a sign chart. I'm going to make a sign chart. So I'm going to put signs of f prime at the top, like we did back when we were doing curve sketching. Signs of f prime at the top, meaning the signs of f prime, which is lowercase f at the top. Well, at -2.5, it is 0. Before then, it's negative. It's 0 at 0. Positive in the middle. Still positive there. Then it's 0 again when x is 4. And then it's negative after that. Then I'm going to put capital F prime signs down at the bottom. Okay. Well, first it's negative slope, and then we have positive slope there from -3 to -2. Then we have 0 slope in that section. Then we have negative slope, and positive 0 slope at x equals 2. Negative slope, and then still negative slope. Okay then. Well then, where is f increasing? Capital F increasing. Well, capital F will be increasing anytime its derivative, which is lowercase f, is positive. Well, its derivative, which is lowercase f, is positive from -2.5 to 0, and then from 0 to 4. So capital F increasing from -2.5 to 0 union 0 to 4, because capital F prime, which equals lowercase f, is positive. And then it's going to be the other way around for the negative. It is decreasing. Where does this whole thing start? Okay, -4 to -2.5, then 4 to 6. -4 to -2.5, then 4 to 6. Because capital F prime, which is lowercase f, is negative in that region. Then where do we have a max or a min? Well, it switches from decreasing to increasing at -2.5. F prime switches from negative to positive at -2.5. So that will be a min. Oh, it's actually about absolute. Okay. Well, the absolute minimax will be, things will either be happening at the relative minimax, which would be at -2.5 and at 4. So we need to know what capital F of -2.5 is. We know capital F of 4. But since it's absolute, we also need to take into account the endpoints. Since it's absolute, we also need to look at the endpoints. So capital F of -4 and capital F of 6. Well, several of these we already found. Capital F of 6 is 2 pi minus 2. Capital F of 4 is 2 pi. Capital F of negative 2.5, we did not find that. But if it would be that -3 and then another -0.5. So that'll be -3.5. And then capital F of, oh wait, no, that was 2 pi. That doesn't, yeah, that wasn't 2 pi. Capital F of -4, what was that? That was 2. -2. That was -2. Okay, well then based on this, 2 pi, that's going to be the absolute max. And then the absolute min is at -2.5. No, sorry, -3.5. So it was at the relative extreme. And then the next section, concave up and down. Concave up. Zoom out so we see this at once. So concave up will be when the second derivative, which here is the derivative of little f, is positive. And that is from -3 to -2, and then again from 0 to 2. So -3 to -2, and then from 0 to 2. And con down from -4 to -3. -1 to 0. Oh, and again from 2 to 6. And so we have inflection points x equals -3. 0 and 2. And then again, I'm not going to graph it. You're not going to have to graph the original. Okay, well, that is section 28. So again, everything that we learned about function analysis, you do have to remember for this stuff. And do I have time to do some problems? Not much. Let's see. Section 32. I was asked about numbers 27 and 30. Section 32, I was asked about numbers 27 and 30. Verse 20. Oh, not in the homework section. Okay, 27's up there. So this number 27, we have e to the x over 2 minus e to the negative x over 2 getting squared. Like problem 20 on the previous page, I'd actually square that. I'd have to multiply it out, FOIL it. So to do so, that would mean we're going to have e to the x over 2 minus e to the negative x over 2 get multiplied by e to the x over 2 minus e to the negative x over 2. And so then that's going to be definite integral from -2 to 2 of e to the x over 2 times e to the x over 2. That's going to add the exponents. And x over 2 plus x over 2, well, if you add half of an x to half of an x, you get a whole x. So that would just be e to the x. Okay, then the outside, the e to the x over 2 times a negative e to the negative x over 2. Well, that would add those two exponents. And x over 2 plus a negative x over 2, well, those would cancel and be 0. So it would be negative e to the 0, and e to the 0 is 1. So it's negative 1. Then the inside, same thing would end up happening. Negative e to the negative x over 2 times e to the x over 2 exponents would add to end up being 0. So it'd be negative e to the 0. E to the 0 is 1. So it'd be negative 1. We already have a negative 1, so really we have a negative 2. And then we have negative e to the negative x over 2 minus e to the negative x over 2. So then it's going to be a plus e to the, okay, exponents will add negative x over 2, and negative x over 2 would be negative x. Okay, now it's doable. So the antiderivative would be e to the x minus 2x minus e to the negative x, variable from negative 2 to 2. Then we plug in the upper limit, so it'll be e squared minus 4 minus e to the negative 2, then minus parentheses, put the negative 2 in, e to the negative 2 plus 4, and then minus e to the negative 2 times negative will make it positive 2. Okay, and so I have an e squared there, and then I have a minus e squared there. Well, those are gonna cancel. Oh wait, no, they won't cancel. They won't cancel because of that minus there. So really that would be 2e squared. That negative will distribute. So it'll be 2e squared minus 8 minus 2e to the negative 2. There we go. That's that answer. So that's 27. And then we're at mass about 30 on the same page. So 30. We are dealing with capital F. We're told let capital F of x be an antiderivative of lowercase of sine cubed of x. And if capital F of negative 1 is negative 4, what is capital F of 4? Well, if I was to take the integral from negative 1 to 4 of sine cubed of x dx, that would end up equaling capital F of 4 minus capital F of negative 1. My mom's calling me right now. I'll have to call her back when we're done. And then at this point, I just add that to the other side. Capital F negative 1 plus the integral will equal capital F of 4. And we're asked for capital F of 4. And this integral, you just put in the calculator. All of these are set up like this where you need the calculator. So the integral from negative 1 to 4 of sine cubed of x dx, you just put in the calculator, math 9. And then capital F of negative 1, we were told is negative 4. So negative 4 plus whatever you get for the integral in the calculator, that will be your answer. Okay. Not much more time. I was also asked about 6.10, problems 1 and 10. So 6.10, problem 1. On 6.10, problem 1, we have the degree on the top bigger than the degree on bottom. With it's quadratic on top and just linear on bottom. Degree on top is bigger than the degree on the bottom. So this is a problem where you would need long division. So you do long division. X plus 1 there, the top one on the inside, x squared minus 3x plus 2. You do your long division. How many times does that go in? X. Give you x squared plus x. You subtract that, x squared is canceled. Negative 3x minus x would be negative 4x plus the 2. Then you do that again. That can still factor in. So sometimes it's x going to negative 4x. Okay. Negative 4 many times. Negative 4 comes out will be negative 4x minus 4. Negative 4x minus negative 4x. Those cancel. 2 minus negative 4. Well, minus the negative would be plus, so that's really 2 plus 4, which is 6. So this integral as is really equals the integral of x minus 4 plus 6, our remainder, over the denominator x plus 1 dx. And then the integral of x, that is easy. That'll be x squared over 2. Integral of negative 4, that's easy. That'll be minus 4x. The integral of 6 over x plus 1, that will be 6 natural log of x plus 1. That's the value of it, plus c. Okay, that's that one. And then on number 10, will require completing the square. Completing the square is required on number 10, where you would factor out that negative to have x squared plus x and plus blank. And then you'd add another plus something here. I'm actually going to put the blank right there, so that the inside of our square root will end up looking like this, because we're going to have a number minus that term squared. It's going to have to be term squared. It's been 52 minutes. These are almost. So here, b is 1, so b over 2 squared would end up being 1 over 2 squared, which is 1/4. So 1/4 would go right there. And then that's really a negative 1/4, and that gets multiplied. So then this just is positive 1/4 there. So then this is really the integral of 1 over square root of 1/4 minus parentheses. Then to factor this, it's always going to end up being x plus the b term. Well, here our b is 1/2. Squared. And then from there, it will end up being an arc sine problem. I'm just going to stop there. Hopefully that one makes sense now. I think I covered every problem people asked. Yeah, well, tomorrow we will be on average value function notes. I hope you have a good day. Bye. See you next week.